Hey everyone, welcome to this explainer. Today, we're putting on our manufacturer hats and talking directly to you, our power plant clients. We're going to dive into how to maximize both the financial and operational benefits of your next major facility design. Because let's be real, choosing the right technology and plant parameters, it's not just some standard engineering box to check. It's literally the financial bedrock of your entire future operation. So let's just jump right in.
Here's our quick roadmap for today. We're going to cover the modern challenge, techno-economic analysis, evaluating alternatives, the capital cost equivalent method, and finally, selecting optimal parameters.
Okay, Section 1, the modern challenge, looking at those big macro pressures.
Look, you are up against some seriously intense market conditions right now. With the global reliance on coal, we're seeing this double whammy, the depletion of reserves and, frankly, an inevitable long-term spike in fuel costs. But it's not just economics, it's heavily regulatory too. Ever since the COP21 Paris Climate Conference laid out those strict CO2 emission targets, the whole world is basically racing toward decarbonization. As a manufacturer, we completely get that these pressures demand highly efficient solutions from you. In fact, technologies that honestly seemed economically unviable just a few years back, they're rapidly becoming cost competitive simply out of pure necessity.
Just to grasp the sheer scale of what we're dealing with here, look no further than the massive pulverized fuel or PF boiler and all that surrounding infrastructure. I mean, we aren't just tweaking a few cells on a spreadsheet here. We're optimizing a colossal, incredibly complex physical system. Every single pipe, turbine, and boiler component represents millions of dollars in capital investment, not to mention ongoing operational costs. So the big question is, how do we actually make the right choice when the stakes are this high?
Right, let's move to Section 2, Techno-Economic Analysis, and how we lower that generation cost.
The absolutely crucial point here is understanding the core trade-off. It's kind of like buying a high-end, super efficient car. To achieve higher steam parameters, which, as you know, is the secret sauce for plant efficiency, you absolutely must use advanced materials. And yeah, that means a noticeably higher upfront capital cost. It's a bigger pill to swallow on day one. But here's the kicker. That increased efficiency massively reduces your fuel consumption. We're talking about a significantly lower operating cost over the entire decades-long lifespan of the plant. Once fuel costs cross a certain threshold, those massive long-term savings completely wipe out that initial sticker shock. It just becomes techno-economically a no-brainer to upgrade.
Section 3, Evaluating Alternative Technologies. Let's look at your financial toolkit.
As your manufacturing partner, we've got a few distinct ways to help you figure out which technology is going to yield the absolute best ROI. The four main methods on the table are the total present worth method, the capital equivalent method, the levelized annual cost method, and the capital recovery period method. Now, they all have their own specific merits, especially depending on if you're swapping out parts or building a whole new plant. But today, we really want to zero in on one in particular because it provides incredible clarity when you're selecting thermal cycle parameters.
That brings us to Section 4, the Capital Cost Equivalent Method. This is actually the evaluation philosophy championed by major utility leaders like NTPC. Okay, so let's break down what this definition actually means for your bottom line. The Capital Cost Equivalent Method is brilliant because it translates long-term operational performance straight into your initial price tag. Instead of looking at two different capital costs and then, kind of vaguely guessing at operational savings over the next 20 years, this method takes those annual operating cost variations, things like improvements in your heat rate or steam generator efficiency, and directly converts them into an upfront capital number. You literally just add this equivalent number to your base capital cost. The result? You get the true total evaluated cost of that alternative. It lets us compare highly complex technologies right on day one, totally apples to apples.
Let's see how this actually plays out in the real world. When we shift your plant to higher steam parameters, it kicks off this amazing domino effect. Okay, yes, your main plant cost increases. We have to use those advanced heat-resistant materials, right? But check this out. Your balance of plant cost actually drops. Because the whole system is more efficient, you're burning less coal and generating way less ash. That means you can get away with smaller, cheaper handling systems. On top of that, your auxiliary power consumption goes down too. The capital cost equivalent method captures all these moving parts mathematically. It basically proves that spending a bit more on the main plant upfront often saves you millions everywhere else down the line.
All right, Section 5, Selecting Optimal Parameters. Let's get to our actual recommendations for you.
Now, to really appreciate where we're headed, we've got to establish our baseline first. For a long time, the industry standard has rested pretty comfortably on traditional 500 megawatt subcritical units. For these conventional 500 megawatt baselines, we're typically looking at a main steam pressure of 170 kilograms per square centimeter. The main steam temperature sits at about 537 degrees Celsius, and the reheat steam temperature is pushed just a bit higher to 565 degrees. For decades, this was the absolute workhorse of the industry. But given those macro challenges and the techno-economic realities we just talked about, honestly, this baseline just isn't going to cut it anymore if you want to future-proof your investments.
So, as your manufacturing consultants, here is what we strongly advise. Pivoting to the upgrade. We're talking about highly efficient 660 and 800 megawatt ultra supercritical units. We really see this as the definitive future of power generation. Let's take a look at just how drastically those parameters need to shift to unlock this new, highly profitable tier of performance.
270. That is a massive jump in main steam pressure required for these advanced plants to run optimally. We are leaping from 170 all the way up to 270 kilograms per square centimeter absolute pressure. I mean, that's huge. But this intense pressurization is the absolute key. It's what allows us to extract significantly more work and energy out of the exact same amount of coal.
And right alongside that intense pressure, we have the temperature, 600 degrees Celsius. We are now targeting 600 degrees for both the main steam and the reheat steam. Now, operating at these extreme thresholds, yeah, it strictly requires those advanced materials we discussed, which definitely drives up your initial main plant cost. But what it unlocks is just unprecedented efficiency. It aggressively drives down fuel consumption and emissions, getting you right in line with those COP21 targets. When we run the numbers through our cost of generation calculator, the ultra supercritical parameters win out every single time. They literally yield the absolute lowest long-term generation cost.
So I'll leave you with this ultimate question. Is your plant ready to invest in the ultra supercritical future? We know for a fact that the upfront capital for 270 pressure and 600 degrees temperature absolutely pays for itself through massive operational savings. The technology is proven, and the financial case, it's crystal clear. I highly challenge you engineering and finance teams to apply this exact analysis to your next major upgrade. Let's build a more efficient, profitable future together. Thank you so much for joining me for this explainer.